Have you ever, really thought about how we actually know what we know about the universe?
Yeah, yeah.
It's like we look up at the night sky, right? See all those stars, and
Right.
we're just tossing around these huge ideas about black holes and galaxies billions of light years away.
Hmm.
How did we even get there
Yeah.
to those stories? I mean, it's crazy when you really think about it.
Oh, it absolutely is. I think it's like that need we all have, right? To figure out where things begin,
Yeah.
Origins, that's like a fundamental human thing.
Yeah.
And I think on one level, it makes sense logically,
Hmm.
like trying to understand something without knowing where it came from.
Right.
It's like trying to read the last page of a book and figure out the whole plot.
Totally.
And then, there's that emotional side too.
Yeah.
Like when we look up and contemplate the vastness of the cosmos,
Mm.
thinking about its origins, it kind of mirrors our own search for meaning.
Exactly. And that's exactly where we're heading today. We've got Neil deGrasse Tyson's Origins, 14 billion years of cosmic evolution
Okay.
as our starting point. And just to be clear, we're not doing like a cosmic cheat sheet on the Big Bang.
Right.
Our mission today is to dig into something even deeper. How we came to know anything about the universe's origins in the first place.
Okay. Yeah.
And it turns out skepticism is a key player in that whole story.
That's right. So the whole foundation of science rests on this idea of organized skepticism.
Okay.
It's this constant methodical process of questioning and doubting everything.
Which honestly feels a little weird, right? Like,
Yeah.
as humans, our first instinct isn't to be constantly suspicious of everything,
Yeah.
especially stuff that really smart people already figured out.
Exactly, yeah. It's almost like it goes
Yeah.
against our nature. We have to actively look for flaws in other people's conclusions to make sure they really hold up under scrutiny. We can't just take someone's word for it.
It's like having that friend, the one who always asks, but why? About absolutely everything.
Right.
Except that friend is the entire scientific community, and they have these crazy powerful telescopes.
Yeah, I like that analogy.
Yeah.
And here's where it gets really interesting.
Okay.
There's a kind of reward system built right into science.
Okay.
If you can find a mistake in someone's work or present strong evidence against an accepted idea, that's seen as a valuable contribution. The book even calls it a noble deed, though that might be a little much.
Wait, seriously, that sounds kind of cutthroat, like everybody's just out to steal each other's research grants.
It might seem that way from the outside, but really, it's more like a team working together on this super complicated puzzle.
Mm.
Everyone benefits when the picture gets clearer. The book compares it to a Zen master correcting a novice, which, might be a bit dramatic.
Right.
But it does get at this idea of refinement, pushing for deeper understanding.
Yeah.
And it's worth noting, this kind of rigorous correction usually happens between people who are already on the same level. It's not so much about taking someone down, but more about collectively making sure we're all on the right track.
So instead of being all defensive when someone questions your work, you're supposed to be happy because it means you're getting closer to the truth.
It might not feel great at the time, that's for sure.
Right.
But the system's built so that finding errors, coming up with better explanations, that's what gets rewarded. And that's how science ends up correcting itself over time.
Mm.
It's like having this constant spell check running on our understanding of the universe.
So it's not just a bunch of scientists sitting in their ivory towers, agreeing with each other and nodding politely at each other's theories.
Not at all, no.
Yeah.
It's a collaborative effort, for
Yeah.
sure. But the book makes it very clear science is definitely not a mutual admiration society.
Right.
And it shouldn't be.
Yeah.
It's just as much about disproving ideas as it is about coming up with new ones.
Right.
It's that constant back and forth that drives real progress.
Okay, let's break this down a bit. How does this whole skeptical approach, this constant questioning, actually play out when we're trying to understand something as massive as the Big Bang?
Well, it all comes down to this cycle.
Yeah.
You come up with an idea, then you test it rigorously against observations and experiments, and then you have to be willing to change it or even completely throw it out if the evidence says you're wrong. Take the Big Bang Theory, for example.
Okay.
It wasn't just some random thought someone had. It came about after decades of observations, like seeing that the universe is expanding, combined with a ton of theoretical work, and it's still being tested and refined as we get more data.
So we're talking about the very beginning of everything, right? With
Yeah.
all the fundamental laws of physics, matter, energy, space, time, all crammed together.
Yeah.
And when we apply those physics rules to the universe as a whole, that's what we call astrophysics.
Exactly. And to understand the universe, going all the way back to those first tiny fractions of a second, we use one of the most powerful tools we have, Einstein's famous equation EPCMR.
Ah, the big one. Yep.
Energy equals mass times the speed of light squared. I mean, you see that equation everywhere, T-shirts, mugs.
Right.
But what does it actually tell us about the Big Bang?
Well, it's considered incredibly powerful because it basically says that mass and energy are fundamentally the same thing. They can be converted back and forth. It's all about this fundamental equivalence. Einstein actually published it as a very short follow-up to his super important paper on special relativity way back in 1905. He even suggested that if something gives off energy, its mass should decrease. And he proposed testing this with radium salts or something like that.
So in that super hot, super dense early universe, we're talking about energy just spontaneously becoming matter and matter dissolving back into energy all the time.
That's exactly it. It was happening constantly in that first unbelievably tiny fraction of time after the universe was born. And as the universe expanded and cooled really fast, the fundamental forces that control everything started to differentiate.
So it's like they peeled apart from each other, like layers of an onion or something. That's a great way to picture it. At the very end of what's called the Planck era, which is this insanely short amount of time, around 10 seconds, gravity was the first force to split off. Then, as the universe kept cooling super fast, past 10 seconds, the forces that were still unified split into the strong nuclear force and what we call the electroweak force. Then, just a little bit later, that electroweak force split again into the electromagnetic force and the weak nuclear force.
So in less than a trillionth of a second, we go from this one unified force controlling everything to the four separate forces we see today: gravity, electromagnetism, and the strong and weak nuclear forces, each one governing different parts of how the universe works.
Exactly right. And during all this force evolution, the early universe was also packed with fundamental particles. Quarks, leptons, and their antimatter partners, plus the bosons, which are the particles that carry those forces.
Now, quarks and leptons, those are like the tiniest building blocks of everything, right? And they come in these different types, almost like flavors. You've got up and down quarks and electrons and neutrinos as types of leptons. And if I remember correctly, quarks don't usually exist on their own, right? They group up to form bigger particles like protons and neutrons.
That's exactly it. Now, what's really fascinating is this slight imbalance between matter and antimatter that existed in the very early universe. At the beginning, scientists think there was basically the same amount of matter and antimatter. But for reasons we're still trying to understand, there was this tiny excess of matter, like one extra particle of matter for every billion particles of matter and antimatter.
1 in a billion. Doesn't sound like much. Almost statistically insignificant, you know.
It does seem small, but that tiny difference is why we and everything we see around us even exist today.
Wow.
Think about it. All that initial matter and antimatter, they were constantly colliding and destroying each other, turning back into pure energy. But because there was that little bit of extra matter, that 1 in a billion, it survived this huge annihilation process.
So we're basically leftovers from this epic cosmic battle between matter and its evil twin, antimatter.
You could put it that way, yeah. And as the universe kept cooling, dropping below 1 trillion degrees Kelvin, Those quarks started clumping together, forming hadrons, which are heavier particles like the protons and neutrons that make up the centers of atoms. This change from free quarks to these bound-up hadrons, it locked in that tiny matter-antimatter imbalance.
Okay, and what happened next? More cosmic demolition derbies with particles and antiparticles smashing into each other.
Exactly. The next big annihilation event was between electrons and their antimatter counterparts, positrons. Once again, almost all of them vanished in bursts of energy, filling the universe with photons, which are particles of light. But again, a small fraction, about 1 electron for every billion, managed to survive.
So at this point, the universe is basically a set recipe, right?
Right.
A bunch of protons, a slightly smaller number of electrons that'll eventually join them, and a whole lot of photons zipping around.
That's the picture. And as the temperature kept falling to below about 100 million degrees Kelvin, those protons started fusing with other protons and neutrons, creating the first atomic nuclei. About 2 minutes after the universe began, most of it was made up of hydrogen nuclei, with around 10% helium nuclei, and then tiny amounts of deuterium, tritium, and lithium.
Okay, so we've got the centers of atoms, but not complete atoms yet, right?
Not quite. For about the next 380,000 years, the universe was still too hot and dense for atoms to fully form. It was this hot, opaque soup of those nuclei, along with free electrons and photons. The electrons were roaming free, constantly bumping into and interacting with the photons.
Sounds pretty chaotic.
Yeah, it was. The universe was opaque during this time, like a thick fog.
Yeah.
But when the temperature finally dropped below about 3,000 Kelvin, something really important happened.
What happened?
The electrons finally had low enough energy to be captured by the positively charged nuclei, forming the first neutral atoms. And this merging of electrons and nuclei changed the universe from opaque to transparent.
So the fog cleared, like literally.
Exactly. Since the electrons were now part of atoms, they stopped scattering those photons. The photons were free to travel across the universe, and they've been traveling ever since. This light, stretched out over billions of years by the expansion of the universe, is what we now observe as the cosmic microwave background radiation. That moment, when atoms formed, that was when the formation of particles and atoms in the early universe was complete.
Okay, so we keep talking about matter and antimatter, like they're these two sides of the same coin. We have a pretty good grasp on matter, but what exactly is antimatter?
Well, basically, for each fundamental particle, there's an antiparticle. They have the exact same mass, but they have opposite values for certain properties, mainly electric charge. So, an electron has a negative charge, its antiparticle, the positron, has a positive charge.
Okay, opposite charges. That makes sense. But what about particles that don't have an electric charge, like the neutron? Does it have an antimatter version with like opposite zero charge?
Yeah, it does. It's called the antineutron. Now, this opposite zero charge thing, it's a bit of a simplification. It has to do with the quarks that make up these particles. A neutron is made of 3 quarks, and their charges add up to 0. An antineutron is made of 3 antiquarks, and their charges are opposite to the regular quarks, but they also add up to 0. So same total charge, but the building blocks are flipped.
Okay, that's kind of mind-blowing. Like a mirror image, but on a fundamental level. So how does antimatter even appear? Does it just pop into existence out of nowhere?
It can. If you have a gamma ray photon, which is a high-energy form of light, and it has enough energy, it can actually turn into an electron-positron pair. It's basically pure energy becoming matter thanks to EMCST.
Whoa, like turn of light into stuff.
It's not magic, but it's pretty close. In one way of looking at it, you can think of a gamma ray kicking an electron out of a negative energy state, which leaves you with a regular electron and a hole where the electron was. This hole is what we call a positron. And the reverse can happen too. When a particle and its antiparticle meet, they annihilate each other, filling the hole and releasing energy, usually as gamma rays. As the book mentions, gamma rays are definitely something you want to avoid.
So if this matter-antimatter annihilation releases so much energy, could we use that somehow? Like, could we build super efficient antimatter engines? I feel like I've seen that in Star Trek.
The idea is really appealing. The amount of energy released during matter-antimatter annihilation is huge, which would make it a really efficient fuel. But the problem is, making and storing antimatter is incredibly difficult. It doesn't just exist naturally in large amounts in the universe as we know it. Even Captain Kirk in Star Trek was always asking Scotty for more power from their matter-antimatter warp drive, which tells me it wasn't exactly a self-filling gas tank. Without a readily available source, a truly self-generating antimatter engine would mean we're breaking the law of conservation of energy.
Too bad. So no warp drive to Alpha Centauri anytime soon. But what about just studying antimatter? It seems impossible if it disappears the second it touches normal matter.
Yeah, it's a huge experimental challenge, but physicists around the world are doing amazing work, creating and trapping tiny amounts of antihydrogen atoms, which is an antiproton bound to a positron in special vacuum chambers using magnetic fields. They want to study its properties in detail to see if antihydrogen follows all the same rules of quantum mechanics as regular hydrogen.
And what about gravity? Does antimatter follow?
That's a great question, and one that scientists really want to answer. Everything we know about physics says antimatter should experience normal gravity, just like regular matter. But proving that is really hard because gravity is such a weak force at the atomic level. We'd need a large amount of antimatter to really see how it interacts with gravity.
So imagine a pool table, right? But
Okay.
everything's antimatter. The table, the balls, everything. And you're playing pool in an antimatter universe. Would it look any different from a regular game of pool until, like, one of those antimatter balls hit something made of regular matter?
Exactly.
Yep.
And an antimatter planet would orbit an antimatter star, just like our planets orbit the sun. This makes sense, and it fits with our current understanding that the fundamental properties of antimatter, like how it interacts with gravity, how it collides, how it emits and absorbs light, should all be the same as ordinary matter.
Which is a bit unsettling, right? Like, if there was an entire antimatter galaxy hurtling towards us, we wouldn't know until it was too late.
True. We wouldn't be able to tell it apart from a regular galaxy until they collided and annihilated each other, which would be this huge, violent event releasing massive amounts of energy as gamma rays. Imagine two stars the size of our sun crashing into each other and completely annihilating. The resulting burst of light and energy would be brighter than hundreds of millions of galaxies combined, and it would only last for a short time.
That's terrifying. So, have we ever seen anything like that happen in the universe?
We have no evidence of such a large-scale matter-antimatter annihilation ever happening, and that's a strong indication that our universe has been mostly made of regular matter since the very beginning. So while the idea of colliding with an antimatter galaxy is great for sci-fi, it's not very likely in our real universe.
Good to know. Okay, so we've talked about the Big Bang Theory and all these tiny particles, but what's the evidence for this? It can't just be a bunch of equations.
Oh, definitely not. One of the biggest pieces of evidence is something called the cosmic microwave background radiation, or CBR for short. Predicting this radiation was a huge challenge for another theory, the steady-state theory, which said the universe was eternal and unchanging. The fact that CBR exists tells us the early universe was very different, very hot, very dense, and rapidly expanding.
Okay, and how did we even discover this ancient light from the Big Bang? It seems impossible.
It was actually a lucky accident back in 1964. Two scientists, Arno Penzias and Robert Wilson, were working at Bell Labs and kept picking up this persistent background noise with their microwave antenna. They called it excess antenna temperature and couldn't get rid of it no matter what they did. They even cleaned pigeon droppings off their antenna, thinking that might be the problem.
Wow, what a humble beginning for such a major discovery. And they got a Nobel Prize for it, right?
They did. And here's the really interesting part. At the same time, there was a team at Princeton University, led by Robert H. Dick, who were building a detector specifically to look for the CBR. They were working based on predictions made by George Gamow, Ralph Alpher, and Robert Herman decades earlier.
So the Princeton team was looking for it, while Penzias and Wilson just stumbled on it while doing something else entirely.
Exactly. The Princeton team had the theory, but they didn't have the fancy equipment Bell Labs had, so they were moving slower. And when they heard about Penzias and Wilson's unexplained microwave signal, they immediately knew it was the CBR they were looking for.
Ouch, they must have been so close. A true scientific scooped moment.
It happens. But the important thing is, Penzias and Wilson's measurements of this background radiation matched the predictions. Its temperature, how evenly it spread across the sky, and the fact that it didn't seem to be coming from any particular direction in space. It all fit together perfectly and provided huge support for the Big Bang theory.
So this faint microwave radiation is like a baby picture of the universe from when it was just 380,000 years old.
You got it. And studying this radiation has become incredibly precise. We have so much data from space missions like COBE, WMAP, and Planck, which have mapped the CBR in amazing detail, showing tiny fluctuations that tell us about the seeds of galaxies and the large-scale structure of the universe. Cosmology has turned into a real precision science.
It's crazy to think that those tiny variations in the oldest light in the universe can tell us so much about its history.
It really is. And it all comes back to that idea we started with. Our understanding of the universe's origins isn't just about looking at cool pictures of galaxies. It's built on this foundation of constantly questioning, testing, and challenging our ideas. And it's about giving credit to those who can refine our knowledge or even prove us wrong. That's what gives us confidence in exploring the universe and understanding its origins.
So next time you hear some fact about the universe, take a minute to appreciate all the scientific skeptics who have worked so hard to make sure it's actually true. It makes you wonder, what other things that we think are just the way things are might actually be the result of some hidden, unexpected process? Food for thought, right?
Yeah, for sure.